this webinar, in the next half an hour, I want to show you how to use trace to debug without breakpoints and to investigate the runtime behavior of the application, for example, to identify timing issues or bottleneck in your application. And that's with trace. So trace is a methodology or a technology that has become more and more important for debugging and runtime analysis in the last years. Trace is a hardware feature that can be found on many of the microcontrollers that are used right now, and sometimes it comes with a small feature set, and sometimes it is very powerful, and it's an addition to production devices, and sometimes you have dedicated trace devices like we see on the Aurix. In general, trace is very useful when you need a deep insight into the runtime behavior of your application. It allows you to observe the execution of code, of functions, or even tasks if an operating system is in place, or you can view the data transfers over the different system buses. While the system is being traced, all the data that are recorded are generating trace messages, and these trace messages are then output as a trace stream to the tool. So the trace messages itself or the trace stream can either be stored in the device itself in an on-chip trace memory, if the device has one, or the trace stream can be transferred directly via the trace probe of the debug tool into the debugger, and then you need the dedicated trace interface. The key feature of trace is that you can do the observation completely non-intrusive. That means you have no influence on the runtime behavior by using trace. You can debug without interrupting the target, and you can do this at full target speed at the, in most cases. And you can do very accurate time measurements thanks to trace. That makes it very interesting if the timing of an application should be analyzed. So let's have a look at the trace system of the Aurix microcontroller from Infineon. This is called the MCDS, and this stands for multicore debug solution. So MCDS is a part of the so-called emulation extension of the Aurix, which is an additional part, and it is not part of the production chip. So you will find no trace capability if you have a production device or an ECU. So only special development devices provide the trace. So and these are called the emulation devices, and the emulation devices which has the trace capability are pin compatible to the production chip. So that's very important if you design your PCB. The MCDS contains trace observers called the POB or BOBs, and the multiplexer for selecting the trace sources. So trace sources can be cores, buses, or peripherals. The observers monitor the program execution or the data transfers of the selected trace sources and generate the trace messages. Each of the observers provided trigger and filter units that allows you to reduce the amount of generated trace data. So you simply select which data should be, or which information should be traced and output to the trace memory or to the via the trace interface. There is also a cross trigger unit that allows you to distribute events between the observers, and together with the triggers and filters of the observers, you can realize very specific trace tasks. For example, you can enable the program trace on one core if an interrupt service routine on the other core is entered. The emulation devices of the Aurix provide a dedicated on-chip trace memory for saving the captured trace information. The size of this memory is up to 2 megabyte. The actual available size depends on the device. So there are devices with smaller sizes of trace memory, and the largest one is, for example, comes with the TC39, the 6-core Aurix microcontroller. If you use the trace memory, then you can transfer the captured trace information using the DAP, the debug interface of the Aurix, to the tool. So in this specific case, you don't need any special debugger hardware with a trace interface or a external trace memory. So from our access device family shown here on the bottom, yeah, here you can show that. You can see the devices of our family. You can even use the smallest one, the UDE2 Pro, which is also the base device in our family here, and has no dedicated trace memory. For some of the Aurix development devices or emulation devices, we have a serial trace interface, the HEBT. This HEBT can be used to get the trace stream directly off chip. It is based on the Aurora protocol and can transfer the data at 2.5 gigabit per second. And for that, we provide also devices supporting the HEBT, the UDE2 Next, this black one, or the UDE3 Plus, the white one, support the HEBT by dedicated trace modules or trace pods. And also they have a trace memory implemented there. So 512 megabyte for the UDE2 Next and up to 4 gigabyte trace memory for the UDE3 Plus. From the debugging perspective or from the use case perspective, there are two use cases basically for tracing. The first use case is trace-based debugging, and the second one is trace-based runtime analysis. Trace-based debugging is basically useful if you try to find bugs that are caused by parallel execution or by timing problems. In general, whenever the debug tool would or the access to the target by the debug tool would possibly hide these bugs. So if, for example, if no breakpointing is allowed. So you can use trace if you have to avoid any influence on the runtime behavior by the tool. Another use case is whenever you need more than a snapshot of the target state. For example, if you hit a breakpoint, then you see only a snapshot at this specific point in time. And if that is not enough, then and if you want to look back in time, then trace is useful. And then we have trace-based runtime analysis. So trace-based runtime analysis covers a lot of useful things to analyze the runtime behavior of your application. For example, if you want to do profiling, if you need the core graph analysis, if you want to visualize the execution of the program or of task during the time and so on, then trace is very useful. So now it's time to have a look at the UDE, at the tool, to see how trace can be used for debugging and also for investigating timing issues. Before we go into the examples, there should be a general remark on the hardware setup that I use for the demos. I'm going to use the Aurix TC39 emulation device. The examples that I'd like to show you do not require a very large amount of trace data to be recorded for the debug task and for the analyzing tasks, and therefore the on-chip trace memory that we have on the Aurix is completely sufficient, and I can go without any use of the HEPT, and also the UDE does not need any external trace memory. So that's why I use the base device shown here on this image of our universal access device family, the UAD2 Pro, which has no trace memory, and so the data has to be stored on chip. So the UAD2 Pro is connected to my PC using a USB, and to the target board, which is the TC39 emulation device mounted on a tri-board, is connected to the debug tool using this combined JTAG DAP adapter here shown here, and this is connected to the DAP connector on the board. That is the debug interface. So the adapter itself is the only device-specific part here in this debugger setup. That means you can also use the UAD2 Pro for other target devices like ARM Cortex or RH850 or whatever. As mentioned before, the trace is recorded to the internal trace memory of the Aurix, and then we are using the DAP to transfer the data to the tool without the need of any intermediate storage here in the device. So the transfer is directly into the debugger software, the trace software. So the first example that I like to show you is a debugging task. The application that we have is running into a trap, and we want to find the reason for that trap. Now I switch to the tool, which is the UDE, our universal debug engine, and I have already loaded a debugger session, a workspace here with an application flashed into the flash memory, and I can now start the application. You see some variables are updating here, and I can now issue a trap or something that results in a trap, a bus error in that specific case, and we want to find the reason for that. We can look at the call stack. So we see the call stack is very short because we hit the trap from the main function of the core 0 here. But if I go to the core 0 at this specific place here or location, then and we go or we look at the code, then there is nothing that is suspicious and can cause the trap. So it's in that specific case, it makes no sense to do such a stop mode debugging and look at the code here. And to find the trap or the reason for the trap, we are using trace. And the first thing you need to do is to configure the trace task. So basically to tell the trace system what to trace and when to trace. And for that, we have a tool which is called UEC, which is a graphical configuration tool, which allows you to compose a trace task. And it's quite simple. On the left side, you have a library of blocks, of pre-configured blocks. For example, this one, which tells the trace system how much trace memory you want to spend for tracing, and where the trigger is located in the trace memory. The trigger is basically a pin needle in the trace memory, and in general tells you, or tells the trace system when the trace has to be started, the recording has to be started, or when the trace has to be the trace recording has to be stopped. In our case, we want to trace before an event occurred, so we select the post-trigger mode. We select core 0 because we are on core 0 for that. If you use the more complex advanced library that we also provide here, then you are able to perform also a multi-core trace. For example, if you want to see any intercore interaction in the trace, then you can use that library. But for the basic library, the compact one, we have only a single core trace here available. And then we need the trigger condition, which is basically our trap handler here. So we can select this this one. We can select this one, and then yeah, that's all. So basically, we trigger at this if we enter this trap handler here, and everything right before the trigger condition is traced. That is the trace task. But you see, maybe it could be a little bit complex. It's quite simple, but sometimes it's still too complex to handle for such simple trace tasks like history of a trap or something like that. That's why we have new in the next version of the UDE, which is the UDE 2023, which will be released in 2 or 3 weeks or so, a new function which is called simply trace. So I'd like to show you that. I go back to the trap function, and by clicking on a line here in the program window, which is marked with such a blue blue dot, which means for that specific line we have a address available. If I click on such a line, then I get this menu where we find a item configure trace, and I can say, okay, trace to here, and that's all. Then I can I have to reset the target application because we are on the trap here. We restart the target application, start trace. Now the trace configuration is generated and written to the Aurix MCDS unit, and now you see the trace recording has been started, and then I try to enter the trap again, and once I hit the trap handler, the trace recording is stopped automatically. We see some results in the trace window, which is the the representation of the executed machine instructions, or the addresses, or the code, the source code in C or C++ here, and also the functions that are executed. And because we expect that at the very end we hit the trap handler, we go to the very end, we see, okay, here we have our trigger condition. We see we entered the trap handler, which is the last trace message that we get. And right before this entering, there must be the reason for the trap. So we see here the trap vector table, the execution of the vector table. And then we see the core main function, which we have seen also in the core stack. And then we can go a little bit up, and then we see here in this specific line a pointer assignment to a address which looks a little bit suspicious because this is an illegal or non-valid address in the memory map of the Aurix. And you can now double click here on this line and go to the code, and then we see, okay, we have this illegal assignment to this pointer here, and then an assignment to this location, and that is obviously the reason for this bus error. Okay, first example, first bug found. The next one, in that case, I'd like to demonstrate how we can analyze the runtime behavior of the application. And this application has a timing issue and possible performance bottleneck. This is adapted from a real support case that we had. A while ago, a customer came to us with a timing problem and asked us how to find the root cause for this timing problem. And the problem was that a timing constraint was violated. Sometimes, from time to time, a task was not finished in time. And such kind of things happen very often, unfortunately, and therefore I'd like to take a closer look at how to tackle the investigation of such problems. So the application that I will use here in the demonstration of this specific scenario is of course not that what we saw on the customer support, but it imitates more or less the timing problem that we saw. So the is doing the following. It is a simple cooperative scheduler that is running on core 1. That scheduler executes tasks on a fixed time slot base. We have a 10 millisecond task, 25 millisecond, 100 millisecond, and 200 millisecond task. And we observe the correct timing. That means which if the tasks are executed periodically according to the time slot. And if it's not the case, then we get an alarm issued by the SMU, which is the Safety Management Unit. We have an indication of these alarms and get also some additional information which task didn't meet its time slot. So we have a critical path here. That is when all the tasks have to be executed in the time slot. And for this, we have a 10 millisecond execution time that must not be exceeded. There's also a periodic interrupt that is issued by the Capture Compare Unit 6 of the Aurix, and which is also handled by the Core 1, and we will see what happened. Switching back to UDE, I restart the application, and we see here we have this alarm counter here, and this is counting up. That means that we have a timing problem here that is observed by this checker routine for each task. And we see also in the task information structure, we have a block for each of the 4 tasks, that in the case of the 10 millisecond task here, the periodicity is 10 millisecond, we get some errors here, and you want to analyze this problem. And for that, we need to configure the trace again. In that specific case, we have no dedicated function in the simply trace feature, so we need to configure the trace with the UEC. Here you see already also the configuration that was done by the simply trace in this example before, but I clear that and use the compact library again. Doing the same as before, we need the initialization block. We spend all the trace memory that we have. And in this case, a pre-trigger can be used. So we start the trace at a certain condition, and then the trace ends when the trace memory is completely filled. Then we want to observe core 1 because our scheduler is running on core 1, and then we define the trigger condition, which is in that case the core 1 worker function, which is the scheduler of our tasks. And then we can use a nice feature in the Aurix, which is called compact function trace. So by default, we are using branch traces. That means only the branches in the application or the executed branches are traced, and from these are trace messages generated. Everything in between or the sequential code can be reconstructed by the tool. But we need some branches for the reconstruction. So branch trace gives us all the necessary information. But in that case, branches are not required because we want to see or we want to analyze at the function level and not on the statement level here of all the executed functions. So we can use the so-called compact function trace, which allows us to save a lot of trace memory, and it basically generates only trace messages if you have a call or a return. And finally, we need some timing information because we want to analyze the runtime behavior and measure some timings. So we have to enable the tick messages. And then it's a good idea in that specific, in such a case, to enable also a block or use a block that is called interrupt detection, which detects the entering and the leave into interrupt service routines and output some event messages, or they are called watch point messages, into the trace stream that helps the analyzing the the execution sequences and to do the required analyzing task afterwards. Okay, that's all. Then we can start trace recording. Again, the trace configuration is translated into register settings, and these are transferred to the trace tool. And once we stopped, or once the trace has been stopped, we see here the result in the trace window. You see here the result of the compact function trace. Returns and calls are traced, and only left information in between. This is not very useful in this view, so we change to another view, to the so-called call graph analysis. The call graph analysis has to be executed separately. We select the call graph analysis for core 1 and use the start function, and it takes some seconds to analyze the trace stream, and then we get the call graph of all the executed code here. The call graph shows you the relationships between the executed functions. So basically, which function were called from a specific function, or vice versa, from which function a specific function was called from. So you see here the call hierarchy that of the executed tasks, for example. And also here we see, for example, task 25 milliseconds was called by the core 1 worker, and calls the check timing function, toggles the LED, and something else. We have two types of call graphs, the dynamic and the static call graph. The static call graph shows you or in its static call graph, the calls to a function are accumulated regardless of which was the caller, and in the case of the dynamic call graph, the caller is also considered. This has an effect on the call counts that we have here in the square brackets. We get also statistical information. You see this in the tooltips here, like the call counts and also additional information about the execution times. And we have also a tab here providing us profiling information, including the number of calls, including the execution time, inclusively or exclusively of the called subfunctions. And we see all the numbers with a minimum, maximum, and average values. And this can be used here to analyze the runtime behavior. In that case, we select or we sort here the execution time to find the timing issue. And if you look here at the executed functions, then we see that the task 25 milliseconds is at the very top and takes 16 milliseconds. And remember that the critical path was 10 has not to be exceeded by 10 milliseconds. And this gives us the first hint that with the task 25 milliseconds, there is something wrong, because the maximum execution time is 60 milliseconds. So the minimum is 2.6 or 2.7, and the average is 3.3. So that looks like that only a few of the executions of the task 25 milliseconds takes too long. And to analyze this, you can use, we want to see which of the specific executions are taking too long and want to see what happens in between. And for that, I change the representation of the call graph. I change it to the so-called timeline mode, and then I have to start analyzing again. And in the dynamic function tab or profiling tab, I can now see all the single executions of the functions here, also of the task. And if I sort this again by the time, then I see, okay, here we have 1, 2, 3, 4, 5 executions of the 25 millisecond task, which takes 60 milliseconds. But now I can select one of those and go into the graph and see what was actually executed in this for this specific execution of the 25 millisecond task. I use the show in graph function, and this switches to the dynamic call graph here at our task 25 millisecond function. And I scroll a little bit up, and then I see, okay, what was executed. We see the overall execution time of this specific execution. We see, okay, we have executed the check timing. If I double click here, I can show you the code. This is the code here. Going back, unfolded. We execute a LED toggling, which is that one. And then we see that a interrupt service routine was executed, which is not intended here. But this interrupt service routine took more than 13 milliseconds, which is too long for this cooperative scheduler. So that means that the interrupt service routine breaks our execution and breaks our timing constraint that we have for this scheduler. And we have to now to to change the behavior either of the scheduler to be not cooperative anymore, and to deal with such interrupts, or you can move the interrupt handling, for example, to another core. And we can also illustrate this in a graphical manner in the so-called execution sequence chart. I started analyzing also for this tool here. Once it has finished, we see, I zoom to the complete timing range. We see here all the executed functions here over the time. And if I zoom a little bit in, then we see here we have very often a very nice regular execution of our 10 millisecond task, but sometimes this case and in that case we have a gap here in the execution scheme that is caused, if you look a little bit upwards, by the 25 millisecond task, which is again interrupted by the worker of the CCU6 interrupt here. That illustrates the problem that we have. So the task 25 millisecond is interrupted here, sometimes by an interrupt, and as a result, takes too long, and the 10 millisecond task is not executed in this specific time range in the required regular manner. So yeah, we are running out of time. That's all what I want to show you today. I've seen that trace is very useful if you want to debug things where a breakpoint or a stop mode debugging does not help very much. And also tracing is very useful if you want to identify timing issues or bottlenecks in your application.